Okay, welcome back, students. In this video, we're going to learn about an important part of chemistry. It's kind of like stoichiometry. We're going to do a lot of stoichiometry, but we're going to learn a new principle, and it's called limiting reactant. Which reactant out of the two is going to run out first? And we're going to be able to determine that after today's video. And so I will warn you that this gets a little bit complicated. It was somewhat of a hard kind of a concept for students to learn. So please pay attention. Remember, you can go through the video, rewind it, go back and watch it as many times as you need to until you feel comfortable with it. So, all right, let's get started. So limiting reactant, if you look at this slide and this picture here, if we were making, it looks like hamburgers, right? So the reactants here for a hamburger, you've got to have the meat patty, the buns, the cheese, and the tomato. Everyone loves tomatoes, right?
Nope. Right.
Ruben, you like tomatoes?
Yes, sir.
All right. Those are our reactants. We need that in order to make a good hamburger, a cheeseburger. Okay? So if you look at the reactants here, guys, so look at all these reactants. Which one is going to run out first?
The slices of patties.
Yeah, the patties. How many do we have? We only have 3 patties. So can you make more than 3 cheeseburgers?
No, sir.
No. So that right there, because it's the limiting ingredient here, we would call this the limiting reactant. Even though you have how many slices of cheese? 1, 2, 3, 4, 5, 6 slices of cheese. You've only got 3 patties. So you can only make 3 cheeseburgers. So what do we call all the rest of this stuff? Because we got 4 buns, 6
Extras.
cheese. How many tomatoes? 7? Did I count that right?
Yes.
So what do we call all the rest that we don't use?
Extras.
Let's call the excess reactants. Okay? We put those back in the bag and then we use it next time, right? That's the excess reactant. So that's reactant that's not going to be used up. So today we're going to talk about how to determine which is the limiting reactant. And it's going to be a very important skill going forward. So, all right, definition for limiting reactant. It is the reactant that runs out first and thus limits the amount of product that can form in the reaction. So limiting reactant is the one that runs out first and thus limits the amount of product that can form in a chemical reaction. So again, we're limited in the number of cheeseburgers that we made because we only had 3 patties. This one's going to run out first, and so we're limited. That's going to determine how much product we can form. The other reactants that's not limiting is called the excess. So this is just the stuff that's going to be left over when your chemical reaction is done. It's going to be a pile left over that didn't react. Okay. In the following chemical reaction, oxygen, O2 is red, is reacted with hydrogen, which is H2, and that's blue, to form water, H2O. So we've got our oxygen here, so O2 molecule, and our hydrogen, the H2 molecule right here. Which one is the limiting reactant, guys? Oxygen. Okay, good. How many molecules of oxygen do we have? Molecules. 2 molecules. How many molecules of hydrogen do we have? 6. And so you can see over here, which one's the excess reactant then? Which one's left over? Hydrogen's left over. There just wasn't enough oxygen. So oxygen is our limiting reactant in this example. So hopefully you kind of get a sense of what a limiting reactant is. It's the one that runs out first in a chemical reaction. Okay, so our limiting reactant was the oxygen. What is the excess? It was the blue one. It was the hydrogen. Okay. Finding limiting reactant. There's 2 ways to determine the limiting reactant. The first method is use reactant quantities. And that's one that I kind of like the most. And I'm going to use this one the most. But I'm going to show you both ways. Okay? The second method for determining the limiting reactant is use quantities of product formed. Now this works fine. Maybe you'll like it better. I'm going to show you both ways, but I like number one because it's a little bit shorter. It cuts down on some of the steps. So 2 ways to find limiting reactant. We're going to cover both of them in this video. So finding the limiting reactant from quantities of reactants. Let's go over that first method first. Always start with a balanced chemical equation. Got to make sure it's balanced, okay? If it's not balanced, you're not going to get the right answer. Number 2, determine the mole ratio of reactants from the balanced chemical equation. So we're going to determine the mole ratio of reactants. I'll show you what that means here in a second. Step 3, we're going to calculate the actual number of moles available. So the actual number of moles available for each reactant. And then step 4, calculate the mole ratio of the available reactants. So again, we're going to do a mole ratio of the available reactants. This will make sense as we go through an example problem. Step 5, from your answer to step 4, you're going to identify the reactant that is going to be the limiting reactant. Okay, so let's go through an example problem. Please pay attention and be following along in your guided notes as we go through this. So first begin with the balanced chemical equation. Is it balanced, guys? How many nitrogens here? 2. How many here? 2. How many hydrogens? 6. How many on the right side? 6. So is it balanced? Yeah, it's balanced. So it says if you had 200 grams of nitrogen and 35 grams of H2, which reactant would run out first and thus be your limiting reactant? Okay, so let's go back. 200 grams of nitrogen, so I'm starting with 200 grams of this, and 35 grams of hydrogen. So you cannot just look at the mass here and say, oh, this one's 200, so there's going to be a lot of that, and this one's 35. There's not going to be very much, so you can't just look at it and say hydrogen is going to be your limiting reactant. Okay, so let's go through and figure that out. Here's how I would do it, okay? So we do a mole ratio first, and I always put in theory. So put in theory the mole ratio of hydrogen to nitrogen. What would the mole ratio of hydrogen to nitrogen be, guys? 3 to 1. So in theory, there should be 3 moles of H2 for every 1 mole of N2. So there should be a mole ratio of 3. That's in theory. In theory, because that's what this balanced chemical equation is telling us, right? You with me to there? Okay. Now let's see what we actually have. Okay. So we need to determine the number of moles of nitrogen and the number of moles of hydrogen. Can we do that? Gave us grams or mass. So let's start with nitrogen first. We've got 200 grams of N2. We're going to put that over 1. So all we're going to do is use our roadmap to go from grams to moles. Okay? It's just one step, so it should be pretty easy. If grams of nitrogen's on top, where does it go? On the bottom. And we know we want to go to moles, so 1 mole of N2. What's the mass of 1 mole of N2? How many grams? Well, on the periodic table, nitrogen is 14. But how many do I have? 2, so that's going to be what? 28. Okay. My grams of nitrogen will cancel out, and I'm left with moles of nitrogen. So let's figure out what that is. What's 200 divided by 28? 7.14 moles of N2. Right? Okay. Now let's determine how many moles of hydrogen we have. The actual number. So down here, I want you to label this actual. Now, up here it was in theory because going off of the balanced chemical equation. But what we're doing down here is using stoichiometry to see how much we actually have. How many moles we actually have. So look, we did it for nitrogen. Now let's do it for hydrogen. Okay? How many grams of hydrogen are we starting with? 35 grams of H2. Put it over 1. We're going to take this to moles. Grams of H2 is on top. Where does it go? Okay. What's on top? Moles of H2. 1 mole of H2. How many grams is that? Well, hydrogen is 1 on the periodic table, but I've got how many of them? 2, so it's 2 grams. Okay, so how many moles of hydrogen do we have? It's 35 divided by 2. What is that, guys? 17.5 moles of H2. Okay, that's what we actually have in our chemical reaction. We want to do a mole ratio again, but it's got to be in the same order as we did up here. So moles of H2's got to go on top. So I'm going to put actual again. So I'm going to put, because I put moles of H2 on top up there, I'm going to put moles of H2 on top down here. So how many moles of H2 do we have, actually? 17.5 moles of H2. We're going to divide that by the moles of nitrogen. How many moles of nitrogen do we actually have? 7.14 moles of N2. You guys with me to here?
Yeah.
We can do this. Okay. Now let's see what that is. What's 17.5 divided by 7.14? Are you guys getting 2.45? So that ratio actually is 2.45. What should it be in theory? It should be 3 in theory. So now is an important point. You gotta look at this equation and say, which number here is too small? Is it the top number or is it the bottom number? What's making this number smaller than 3? Which one is too small? Okay, let me ask you this. What happens to this number if this number gets bigger? It goes up. So is this top number too small? It is. So H2 is our limiting reactant. What would happen if this number, what would happen to, let me ask you this. What would happen to this number if this number went up? As the bottom number gets bigger, what happens to the answer here? It gets what? Bigger or smaller?
Smaller.
Smaller. As you divide by a larger number, this number will get smaller. So we don't want this to go up. We want this one to go. This one's not big enough. Do you see that? So H2 must be our limiting reactant. And so we just determined that H2 is the limiting reactant. Okay? Does that make sense, guys? We're going to go over a couple more example problems and we'll make sense of it. Okay, that's the first way of finding limiting reactant. The second method would be take it all the way to amounts of product. So I'm going to take this moles of nitrogen and put it over 1, and we're going to go all the way to moles of a product. And so we've already answered the question. We know that hydrogen's limiting. I'm just showing you the other way. If you didn't like the ratio way, here's how you would do it the second way. Okay? And so let's go to product. Let's see how much product we could form if we had 7.14 moles of nitrogen. Okay? Well, moles of nitrogen's got to be on bottom. How many moles of nitrogen do we have in the balanced chemical equation?
1.
1. How many moles of ammonia, which is the product? 2 moles of NH3. Okay. And now let's go to grams of NH3. So 1 mole of NH3. What's its molar mass? NH3. Nitrogen is 14 plus 3 from the hydrogen is what? 17 grams. So let's figure out how much ammonia you could make. So 7.14 times 2 times 17. You'd make 242.76 grams of ammonia if you started with 200 grams of nitrogen. Now let's see how much we could make with the 35 grams of hydrogen. Okay, so I'm going to take this to grams of ammonia. Moles of H2 is on top. We know that moles of H2 has got to go on bottom. How many moles of H2 do we have in the balanced chemical equation? 3. How many moles of ammonia? 2. Okay, got one more step. We know that there's 17 grams of ammonia in 1 mole of NH3. So let's times that through and see how much we could make. 17.5 times 2 times 17. We divide that by 3. 198.3 grams of NH3. So which one is your limiting reactant, guys? Which one makes the least amount of product? The H2. It only made 198 grams of ammonia. So if you want to do it that way, take it all the way to the end and see how many grams of product you would make, your limiting reactant is going to be the one that makes the least. Okay? So what's really happening with this reaction is that you have a bunch of nitrogen, a big huge pile of nitrogen. Well, it's a gas. You have a lot of it. And you have just a little bit of hydrogen. When the hydrogen runs out, what's going to happen to the excess nitrogen? So when these two react with each other, what's going to happen with the excess nitrogen? It's just going to be left there. It's not going to react because there's nothing for it to react after all of the hydrogen has reacted. And so our excess reagent would have been nitrogen. Our limiting reactant is hydrogen. So hopefully that makes sense. We showed you both methods there. I got a few practice problems. Let's keep going through it. It's something that takes some time. But I think you'll get it if you'll stay with me. Okay, practice problem number 37. It says nitrogen gas can be prepared by passing gaseous ammonia over copper 2 oxide at high temperatures. The other product of the reaction are solid copper and water vapor. If a sample containing 18.1 grams of ammonia is reacted with 90.4 grams of copper oxide, what is the limiting reactant? How many grams of N2 will be formed? Okay, this is a good problem. It doesn't come out and give us the chemical reaction, does it? The chemical equation. We have to write it. So let's see if we can write it. Nitrogen gas can be prepared by passing gaseous ammonia. What's ammonia, guys? NH3. So we're going to put NH3 over solid copper 2 oxide. We need to come up with the formula here. What are we writing above copper 2? Plus 2. That's its charge. We're getting that from the Roman numeral. What's oxygen's charge, guys? Minus 2. We do the crisscross. Isn't it going to be Cu? What goes here? 2, and then oxygen, and what goes here? Can I reduce it 2 and 2? To what? 1 and 1. So isn't that just going to be CuO? Okay. Okay, so we have that. We're reacting those two reactants. What are the products going to be, guys? Nitrogen. Are solid. The other products of the reaction are solid copper, so just Cu. Is it diatomic? Nope. So I just keep it as Cu. And water vapor. What's water vapor?
H2O.
H2O. Good job. Okay. Now let's balance it. Okay. Let's see if we can balance it easy. How many nitrogens on the right?
2.
2. So let's put a 2 right here. That gives my nitrogens are good. How many hydrogens do we have on the left? 6. How would I get 6 here? Put a 3. Okay. Now my oxygens on the right is how many? 3. So what do I need in front of this copper oxide? 3. And I need 3 where?
There.
In front of the copper. Is it balanced?
Yeah.
Okay. That's step 1. We've got to start with a balanced chemical equation. Now we can answer the question. It says if a sample containing 18.1 grams of ammonia is reacted with 90.4 grams of copper oxide, which one's limiting? Which one's going to run out first? That's what we want to figure out. Okay. So let's try it. Okay, in theory, I want you to write this down. In theory, we're going to do a mole ratio from the balanced chemical equation. We have 3 moles of CuO for how many moles of ammonia? 2. I'm getting those numbers from the balanced chemical equation. Okay. And so I want that in a decimal form. What's 3 divided by 2, guys? 1.5. So the mole ratio there should be 1.5. In theory. That's what this balanced chemical equation is telling us. For every 1.5 moles of copper oxide, we should have 1 mole of ammonia reacting with it. Okay, in theory. So now let's figure out what we actually have. I want you to put actual now down here. We're going to figure out what we actually have. Okay, we're starting with 18.1 grams of ammonia. So because this was a mole ratio up here, I need a mole ratio of my actual reactants. So that's what I'm going to try and convert this to moles now. Okay, if grams of ammonia is on top, we know that grams of NH3 goes on bottom. In 1 mole of NH3, what's its molar mass? 14 from nitrogen plus hydrogen is 1, but I got 3 of them, so that's 17, isn't it?
Yes.
Okay. And that will give us moles of ammonia. Let's figure that out. So I'm getting 1.06 moles of NH3. So 1.6 moles of NH3. Now let's figure out how many actual moles of the other reagent we have, copper oxide. So it says we started with 90.4 grams of copper oxide. So that's what I'm going to put over 1. Okay, if grams of copper oxide is on top, we know that it's got to go on bottom. In 1 mole of CuO, what's its molar mass, guys? Well, copper on the periodic table has a molar mass of 64, and oxygen is 16. So 16 plus 64 is 80 grams. My grams of copper oxide cancel out. I'm left with moles. Okay, so 90.4 divided by 80 is 1.13 moles of CuO. Okay, now we can't determine it yet. Maybe you can by looking at it. But let's do a mole ratio and see. What did I put on top in my mole ratio up here?
3 moles.
Copper oxide or ammonia?
Copper oxide.
Copper oxide. So I need to put copper oxide on top down here. So this is our actual. So we have 1.13 moles of CuO. So we're going to divide that by the moles of ammonia because I put that on bottom up there. I actually have 1.06 moles of NH3. Okay, now let's take that ratio and put it into a decimal form. So 1.13 divided by 1.06 and I get 1.06. Is that what you guys got? Okay. So now this is the point where you got to ask yourself, which one is too small? Which number here is too small? Remember, we wanted this ratio to be 1.5. This number is not 1.5, it's smaller. So what's making it too small? Ask yourself, if this number got bigger, what would happen to this number? It would get bigger. So this one's too small. Do we see that?
Yeah.
The top number here is too small. Because if it was bigger, it would go up. But it's not. So which one is our limiting reactant? Copper oxide. So copper oxide is our limiting reactant. Okay. So if our limiting reactant is copper oxide, I'm going to make a note of that. CuO is limiting reactant. Okay, we're going to circle that. That's part of our answer. But it also asked us another question. How many grams of N2 will be formed? How many grams of nitrogen will be formed? Now, this is easy. We just take stoichiometry and take it a bit farther. Go across the roadmap and see how many grams of nitrogen will form. But, am I going to start with the moles of nitrogen or moles of ammonia? Or am I going to start with moles of copper oxide to figure that out? Which one's going to run out first, guys? The copper oxide or the ammonia? Copper oxide is going to run out first. So we better figure it out from the copper oxide. You always use the limiting reactant to see how much product you're going to form. Okay? So let's just keep it going. We're going to put that over 1. Now, if you're using a road map, we're at moles of reactant right here, moles of reactant. Now we've got to go across the road map to moles of product. So we're going to use a mole ratio. We got moles of copper oxide on top. So I'm going to put moles of CuO on bottom. We're trying to go to moles of what? What product are we trying to go to, guys? Nitrogen. Yeah. Where do I get this? Where do I get these numbers from, guys? Balanced chemical equation. How many moles of nitrogen are we going to form? Just 1. How many moles of copper oxide are we using here? 3. Okay. Now I'm to moles of nitrogen, but it wanted grams of nitrogen. So we're going to take it one step farther. In 1 mole of N2, how many grams of N2 are there? Well, nitrogen on the periodic table is 14, but I got 2 of them, so that's what? 28 grams. Okay, now that can be finished right there. So we're going to take 1.13 times by 28, and then divide by 3. I'm getting 10.54, so 10.5 grams of N2. Okay, that's a lot of work, isn't it?
Yes.
Let me ask you this question. If I would have used ammonia to figure out how many grams of nitrogen we'd make, would it be more or less than this? 10.5 right here. It'd be more. This is our NH3 is the excess. NH3 is the excess reactant. Copper oxide was the limiting. So we always use the limiting reactant to be able to tell how much product you're going to form. Because the other one is just going to be, there's going to be a lot of it left over. So you're going to have a bunch of ammonia left over in this reaction. Anyway, hopefully that's making sense. I think I've got a couple more practice problems and then we'll be done. Okay, practice problem number 38. Follow along in the guided notes. Here we go. It says ammonia is produced from the reaction of nitrogen and hydrogen according to the following balanced chemical equation. This is a very famous reaction. Okay, we make ammonia. It's a nitrogen product that we can use in a lot of different applications. It says, what is the maximum mass of ammonia that can be produced from a mixture of 1 times 10 to the third grams of nitrogen and 5 times 10 to the second grams of hydrogen. First of all, I'm not really used to using scientific notation. Let's switch it out of scientific notation. Let's do nitrogen first. 1 times 10 to the 3. Which way do I move the decimal and how many spots?
To the right.
3 to the which way?
Right.
Right. So how many grams do we really have of nitrogen? 1,000. 1,000 grams of nitrogen. How many grams of hydrogen do I really have? I move it over 2 times, so that's 500, right? 500 grams of hydrogen. So that's what I would do first. Okay. We have a whole bunch of nitrogen, 1,000 grams, and 500 grams of hydrogen. Now we need to decide which one's going to run out first. In theory, so write down theory, our mole ratio should be, how many grams of hydrogen, guys? Or, sorry, let me rewrite that. 3 moles of H2 for how many moles of nitrogen? 1. Okay? If you take 3 divided, oh, that's nitrogen. Making a lot of errors. Okay. If you take 3 divided by 1, what do you get?
3.
3. So we should have a mole ratio of hydrogen to nitrogen of 3. In theory, that's what this balanced chemical equation is telling us. There's 3 moles of hydrogen are going to react for every 1 mole of nitrogen. Now let's see what we actually have. Actual, we're going to start with our actual amounts. Let's do nitrogen first. So we got 1,000 grams of N2. Put it over 1. Let's take that to moles. In 1 mole of N2, how many grams are there? 28, thank you. My grams of nitrogen cancel out. What's 1,000 divided by 28? Are you guys getting 35.7?
Yes.
Moles of N2. Okay, perfect. Now let's figure out how many moles of hydrogen we actually have. We're starting with 500 grams of hydrogen, so let's start there. Okay. In 1 mole of H2, how many grams do we have? What's its molar mass of H2, guys? 2. Thank you. So what's 500 divided by 2? 250. I think it should be pretty clear to see which one's going to be our limiting reactant, right? But let's go through the same process and see if we're right. Okay, so in actual, we actually have, now we have to keep the same order. I put moles of hydrogen on top. So I got 250 moles of H2. And I put moles of nitrogen on the bottom. So I got 35.7 moles of N2. Now let's do a decimal just to complete this one. So 250 divided by 35.7. I'm getting 7.00. 7.0. Okay. Now in theory, we should have had, this mole ratio should be 3. But when we use our actual amounts, this mole ratio is now 7. It's too big. So how do we figure out which one is the limiting reactant? What's making this number too big? Let me ask you again. If this number on top goes up, what happens over here? It goes up. So I've got plenty of hydrogen. Which one do I not have enough of? The nitrogen. If this number, let me ask you this again. If this number on the bottom goes up, what happens to this one? it gets smaller. Yeah, if this number that you divide by a larger number, this number is going to get smaller. So we need more of the bottom one to get to 3. So we don't have enough of the nitrogen. So let's make note of that. N2 is the limiting reactant. N2 is limiting reactant. Okay, but that's not what the question asked. It says, what is the maximum mass of ammonia that can be produced from a mixture of nitrogen and hydrogen? So we want to know the maximum mass of ammonia. Which one should I start with then? The limiting or the excess?
Limiting.
Always use your stoichiometry should begin with the limiting reactant. Okay, so I'm gonna move it up to here. So we got 35.7 moles of N2. Okay, I'm at moles of reactant if you're following along on the roadmap. Let's continue on to mass of the product. So we got to do the mole ratio here. Moles of N2 is on top. We know that moles of N2 has got to go on bottom. We're trying to get to the moles of the product, which was ammonia, NH3. Guys, where do I get these numbers from?
The balance equation.
Balance equation. Thank you, Ruben. How many moles of N2 do we have in the balance equation?
1.
Just 1. So that's going to be a 1 right here. How many moles of NH3?
2.
2. So 2 goes right there. Okay. Now my moles of N2 cancel out. I'm left with moles of ammonia, but it wanted mass of ammonia. So moles of NH3 is on top. We know that moles of NH3 goes on bottom. In 1 mole of NH3, what's its molar mass? Nitrogen's 14, hydrogen's 1. I got 3 of them, so what is it? 17 grams. Okay. Now we can multiply across. So 35.7 times 2 times 17. And I'm getting 1,213.8 grams of ammonia. Okay. Very important chemical reaction. We were able to figure out the limiting reactant was nitrogen. Then we were able to figure out, because nitrogen runs out first, we're only going to be able to make 1,213.8 grams of ammonia. This is a very important chemical reaction because nitrogen, in its atmospheric form, N2, is not usable by plants. Plants love nitrogen. It's good fertilizer, but they can't use it. So we've got to be able to break this triple bond between the nitrogens here, and this chemical reaction does that and produces a nitrogen-containing molecule that can be used to synthesize fertilizers and has really helped the crop production worldwide. So anyway, very good. We've learned quite a bit. I think there's one more practice problem to go through. Okay, there's one more question here. It says, what mass of the starting material would remain unreacted? So we know we have a bunch of what left over, guys? We know we have a bunch of hydrogen left over, but how much? Could we actually determine how much is left over? It's a good question. Stay with me. How would we determine how much of this hydrogen is going to be left over? Could we use stoichiometry to figure that out? I mean, we know we're going to make this much product. Could we use stoichiometry and go from mass of product back to mass of hydrogen and see how much we actually used? And then from that we could subtract the difference and see how much is left over? That's kind of our process there. So let's do that. So let's start with 1,213.8 grams of NH3. And let's go backwards across the roadmap and go to grams of H2. Okay. So if grams of NH3's got to go on bottom, we know that there's 17 grams of NH3 in 1 mole of ammonia. Okay, now let's do the mole ratio. Moles of NH3. We're going to try and go to moles of H2. Where do I get those numbers from? Equation. We have 2 moles of ammonia, right here. How many moles of H2? We have 3. Okay. Now we're to moles of H2, but I want to go to mass. So in 1 mole of H2, how much does it, what's its molar mass? 2 grams. And that will tell us how much we actually used. So 1,213.8 times 3 times 2. And then we're going to divide it by 17 and also divide it by 2. I'm getting that we actually used 214.2 grams of H2. But how much did we start with? 500. So how much remains? How much remains just unreacted? Well, we take what we started with, 500 grams, subtract off what we used, 214.2, and that will tell us how much remains. I'm getting that's 285.8. Did anybody else get that? Okay. I'm putting that 285.8 grams of hydrogen remains unreacted. So, very good. Last practice problem. Let's see if we can go through this one kind of a little bit faster. It says, consider the following unbalanced chemical equation for the combustion of pentane. Okay, and then it says that 20.4 grams of pentane are burned with 50 grams of oxygen. What mass of water will be produced assuming 100% yield? Okay, you guys got to help me out on this one. Let's go fast. If we were going to balance it, what would you guys do? How many carbons do we need? 5. So let's just see if this works out. We got 5 carbons. How many oxygens on the right side now? 10 plus 1. Okay? Well, that's not going to work because we need an even number of oxygens. So what could I do here? We know my hydrogen's got to be 12. So if I put a 6 right here, help me out, guys. So that gets me to 12 hydrogens. How many oxygens now? So 10 plus 6 is what? 16. What do I need here? An 8. Okay. Are we balanced? That's balanced? Okay. Thank you. If 20.4 grams of pentane are burned with 50 grams of oxygen, what mass of water can be produced? We need to figure out which one's the limiting reactant. Let's do it quickly. So in theory, how many grams of oxygen do I have, guys? 8. Or 8 moles, I'm sorry, moles of O2. For how many moles of pentane? 1 mole of C5H12. What's that mole ratio if you put it into a decimal? It's just 8. Okay. Now let's see what we actually have. Let's start with pentane. 20.4 grams of C5H12. Let's take that to moles. Can somebody figure out the molar mass of pentane for me real fast? 72 grams of C5H12. Does anyone else can confirm that? Okay. In 1 mole of C5H12. Okay. Let's see how many moles we actually have. So I'd take 20.4 and divide it by 72. Are you guys getting 0.283 moles of C5H12? Okay. So let's figure out how many moles of oxygen we actually have. We started with 50 grams of O2. I'm going to put that over 1. In 1 mole of O2, how many, what's its molar mass? 16 for 1 oxygen, but I got 2 of them. 32 grams. Okay. So 50 divided by 32. 1.56 moles of O2. Now, when you get to this point, actual molar ratio here, I got to remember to put it in the same order. I put moles of oxygen on top, so I've got to have moles of oxygen on top here. So 1.56 moles of O2 for 0.283 moles of pentane. What does that come out to be? 5.5, thank you, yeah. 5.5. Now this is where you got to ask yourself, okay? This mole ratio is too small. What is making this mole ratio too small? What would happen if this number got bigger, guys? This number would get bigger as well. So we need more of what? O2. So O2 is the limiting reactant. Okay? But it says, what mass of water can be produced, assuming 100% yield? So if all of the oxygen gets reacted, how much mass of water can be produced? So let's figure that out. What would I want to continue the stoichiometry with? Pentane or oxygen? Oxygen. Why? It's limiting. Thank you, guys. So I'm going to continue it here. Put that over 1. Moles of a reactant. I want to go across the road map. So moles of O2 goes on bottom. We're trying to go to moles of water. Where do I get these numbers from? Moles of oxygen. I had 8 moles of oxygen. Moles of water. I'm going to have 6 moles of water. Okay? But I want to go to mass of water. Let's continue it. Moles of H2O goes on bottom. In 1 mole of H2O, what's its molar mass?
21.
18 grams of H2O.
I don't know where I sit.
Guys, I'm making a video. I'm just finishing it real fast, so you're being recorded. Okay, so now I've got to grams of H2O. Let's calculate that out. So 1.56 times 6 times 18
I can't remember where I sit.
and divided by 8. It's 21.06. 21.06 grams of H2O would be formed. Okay, so I hope that helps. We've gone through, we've shown you how to determine which one is the limiting reactant. And if you have questions, please come talk to me, but hope that helps.